Hey, this is Brock Lemires, and in this video I'm going to give an introduction to electromagnetic waves. Okay, so you can kind of almost think of the birth of electrical engineering as this discovery that electricity and magnetism are linked. Okay, so remember in some of the prior videos we talked about a scientist that was named Michael Faraday, and he was one of the first to discover this linking between these two phenomena. And remember that he was the one that found if you pass a charge through a magnetic field, that charge will experience a force on it, a mechanical force. And so engineers took this information and they were able to say, well, I'm going to move a charge through a wire in the form of an electron moving, and I can actually apply a physical force to that wire. And that gave birth to the motor and in turn the generator. And so we were able to take materials that existed on Earth and apply force to them and get electricity out, or apply electricity to them and get a force out. And so this was kind of the birth of our kind of electrical machines. Later on in the 1800s, another scientist came along named James Maxwell. And he discovered that you could actually have energy that radiated through space, through air, outside of conductors. Okay, so not within wires anymore, but actually through a vacuum, through air. And he discovered that this radiated energy, it was actually made up of electric and magnetic fields that were linked together. And so this kind of gave kind of another kind of component to electrical engineering. And he also discovered that light, the light that we see with our eyes, is actually an electromagnetic wave. And so this was a huge discovery because people didn't understand what light was. And he also predicted that these EM waves, these electromagnetic waves, they existed at all different frequencies and wavelengths, and some of them we couldn't see. And so he predicted that radio waves existed, and that would have been a electromagnetic wave that we could not see, but that we were experiencing and could actually detect using, circuits and other things. Okay, and then finally, another scientist, Hertz, the guy that we named frequency after, he proved that radio waves existed with the spark gap radio, and this was a huge breakthrough because it was like the first time that we actually had proof that these electromagnetic waves existed that we couldn't see. Because until then, a lot of the experiments were done with our eyes. It's like, what is happening? What are we seeing? And so now we're starting to basically understand that things exist that we can't see, that we can actually control and predict. And this gave birth to this new field within electrical engineering, which was kind of the electromagnetic waves. Now let's just think about what happened with these discoveries. So when you start talking about electromagnetism, which is the linking between electric fields or electricity, right? So current, voltage, those quantities, and magnetism. So like north and south poles, this invisible force of attraction. What happens is when you start thinking about what you can do with that gave birth to the field of electrical machines. And so over here you kind of see this image of a motor or a generator that's spinning, and this is a whole component of electrical engineering that has many full careers in it, right? I mean, this is just not a light discovery. This is the electrical power grid, right? This is any DC motor that you have, anything that moves. So this is this whole field, and we call this kind of the component of electrical engineering. These are the machines, the electric machines, or power. Okay, and so that's a whole field within electrical engineering. Okay, and then you have this other field within electrical engineering, which has to do with the electromagnetic field propagation outside of wires. Okay, so not in a circuit anymore. We're going to take the energy and propagate it through space. And the words that we use to describe kind of the study of this within electrical engineering are electromagnetic radiation, obviously, but you'll also hear terms like optics and photonics. And so optics and photonics refer to optics as like optical, right? And so that tends to reflect things that you can see. And then you have photonics, which we'll cover in just a second where that word comes from. But it basically means that this electromagnetic energy travels in the form of what we call a photon, which is a packet of energy, a packet of electromagnetic energy. And then we also, this field right here is also where you see electrical engineers work in the field of wireless communication. So this is things like people who build radios and people who build our Wi-Fi routers and people that are building the 5G networks and doing all sort of satellite communication and imaging. So this whole field exists under the umbrella of electrical engineering. along with electrical machines, which is a whole nother subject. And these two kind of major fields that influence society under electrical engineering all come from the fact that electricity and magnetism are intricately linked. Okay, so having set the stage for that, you immediately must know that in an introductory video, you cannot do justice to any of this. So you can't go into depth of electromagnetic radiation and waves and field propagation and stuff like that. But what we can do is just give a high level motivation for what is this about and how do we actually use it and what exists out there that still needs to be done. So in this video, what I'm going to do is I'm going to rely on this this document, this kind of book or series that NASA came up with, and it's called the Tour of the Electromagnetic Spectrum. And so this is the ISBN or the document code. You know, NASA, everything NASA does is public, right? So this is like a big PDF that they made, and they have videos on their website, and it's just a really cool kind of intro to just like, what is this stuff? What is electromagnetic radiation, and what properties does it have that we are interested in? Okay, so let's get started. Okay, so the photon. We use the term photon to describe a discrete packet of electromagnetic energy. So this is what we use to describe electromagnetic field propagation. And when we draw it out, what'll happen is we typically will draw something like this, where you have kind of like a little sine wave looking thing, and then you have an arrow at the end of it. Okay, and so that right there is going to be the photon. Sometimes you'll see it well, another symbol that you can kind of see is sometimes you'll see people draw it like this, where it's like increasing and decreasing in frequency, and then it has an arrow at the end. And this is kind of a way to kind of just show right away. It's like, well, it's a little packet. Okay, so it's a little packet of electromagnetic energy. And this graphic right here is really, it shows kind of the way that this works. So B, remember, is the magnetic field, and then E is the electric field. So you can think of E as the as the voltage, and B is the strength of the magnetic field. And these things travel, and they are interrelated to each other. So one doesn't exist without the other, and they cause each other to do what the other one does. Okay, so this is where they're linked. And what's interesting about it, this is called a transverse electromagnetic wave, meaning that these are parallel, or they are basically at a right angle to each other. But notice that an important part of this is that it's an AC signal, right? So this is not a DC signal. These have to be moving to exhibit the properties necessary to basically move through a vacuum or move through space. But this is kind of how it would look if you could see this thing. Now here's where it gets a little weird. So a photon behaves like a wave and a particle. Now, what does that mean? Well, it really is a particle in the sense that it's like a thing that's cruising along. Okay, so it is just like a little, if you took a little, I don't know, a little ball and tossed it, okay, it moves. But it also has properties of a wave in that it has, you know, a wavelength and a frequency to it. So it does look like a little sine wave. And this becomes really interesting when you look at like the behavior of it and how it interacts with other materials. And so that's something that we kind of come back to. And it really is a fascinating and bizarre thing. Okay, which we probably won't cover in this video. Okay, and it doesn't have any mass. Now this is important. It is not matter. All right, so this is not an electron that is cruising along like we have in wired circuits. When you have a circuit using copper and semiconductor materials and stuff like that, you move charge in the form of electrons, and electrons have mass. This does not have mass. This is literally an electromagnetic field, okay? It is an electric field and a magnetic field that are related to each other. It is energy that is radiated through space, and it doesn't have mass. But it does have momentum. Okay, yet another odd thing about this is that even though it doesn't have mass, it does. They do say that it has momentum, and that comes into play when you look at like how energy is imparted on things that it strikes. It travels the speed of light in a vacuum. So this is literally light. And it really is. We'll talk about that in a second. But this thing's cruising. It's going as fast as you can possibly have in a vacuum. If it is not in a vacuum, it slows down. Okay, so it doesn't travel the speed of light if you are in like air, but it only travels in the speed of light if you're in a vacuum or like in outer space where it doesn't hit anything. Now, here's what's really interesting. It goes forever unless it hits something. And now this is the thing that just blows my mind, and I just can't get over it. This is how we're able to talk to spacecraft that are beyond Pluto right now. Because I'm sitting here with my cell phone and I drive like 15 minutes out of town and I lose service. Yet NASA is talking to spacecraft that are out of our solar system. And it's like, how is that possible? Well, it turns out that it's because the electromagnetic waves that we use to communicate with our satellites or our spacecraft, they're going through outer space and they're not hitting anything. So even if there's a little bit of space dust, it's very unlikely that photon will actually hit it and be attenuated or be like bounced in a different direction. So that's why it works. That's why we're able to communicate for such large distances in space. When you talk about your cell phone and you're like, how come I can't get a signal? Well, it turns out that when you're on planet Earth, there's things that get in the way. So imagine that you go behind a mountain. Well, the little photon hits the mountain and it hits a tree, right? And it doesn't travel anymore. Another thing is that if you get far away from, let's say, the antenna that's transmitting it, it can actually be attenuated by the air. And it can be attenuated by things in the air. So if there's like smoke or like aerosols. So there's a whole lot of reasons why it doesn't transmit forever in our atmosphere. But if you weren't in the atmosphere, it does go forever. So it's a really fascinating thing. Okay. The photon has some characteristics about it that we always talk about. So number one is it has frequency, and number two is it has wavelength, and the frequency and the wavelength are related to each other by this equation. C is equal to the frequency times the wavelength. Now, frequency is given a new little symbol called nu, which is like a little V looking thing right here, but it's not an F, so it's not the frequency that we've learned before, even though it has the same units, which are hertz or 1/2. But we use this nu to basically indicate right away. We're not talking about frequency in a wire. Okay, we're talking about frequency that is propagating as an electromagnetic wave, and frequency is nothing more than how many cycles per second are occurring in this little photon. So if you really have this photon that's like this, it's pretty easy. You just come along, you go like, well, from the like edge to like edge, that's an amount of time. Okay, and then that's going to be 1 over. That's a period, and that's 1 over that, and you get your frequency, and that's it. And this also has something called wavelength, which is related to it, and it's basically the distance from crest to crest, or trough to trough. But it's basically a property of like how far are these things apart? And it's like, man, that's a weird thing to talk about when you're talking about a distance of something that's electromagnetic, and the answer is yes, because this thing really is like this wave that you generated and now it's traveling. Okay, so there really is a distance that exists between these two crests right here, and that is related to the frequency by this equation. Now this is the ideal equation, so it's the speed of light is equal to frequency times wavelength. Like I said though, if you are in a vacuum, this is the correct equation. If you're not in a vacuum, then the speed of light will slow down. Okay, so it won't be the speed of light, it'll be something less. But a photon, whenever you talk about photons or electromagnetic energy, the first thing everybody says is, what frequency are you at? And usually they always say, what wavelength are you at? Okay, but they're interrelated to each other. Okay, all right. They have energy. Okay, this is a moving wave, and it does have energy. And it turns out that the energy is related to the frequency. So this is the equation for the energy of a photon. So it's Planck's constant, which I won't give her here, but it's like this number, just a fixed number. And then you have the frequency, and the energy of a photon is given in 2 different units. That's why I don't give the Planck's constant, because it's different depending on whether you use joules, which is what we think about. But usually we talk about electron volts. And electron volts is basically just a conversion factor so that we can use numbers that are really, really small if you use joules. But we can, instead of saying like times 10 to the negative 18 for all the time, we can talk about something that's like, well, 3. Okay, it's like 3 electron volts. So it's just a conversion factor. It's kind of like saying kilowatts or something like that. Okay, so that's the energy. And there are all sorts of frequencies and wavelengths of electromagnetic radiation or photons. And so this is the classic thing that you always see when you talk about photons and EM waves, and it's the electromagnetic spectrum. Okay, so a spectrum is basically a classification of something on a scale between 2 extreme opposite points. And the extreme opposite points here are going to be a very, very slow frequency, okay, and a long wavelength, or a very high frequency and a very, very tiny wavelength. Now, here is what is awesome. These photons exist at different wavelengths across this spectrum, and some of them we can see with the human eye. And so you always see this thing right here where you have like this rainbow in here. Well, this represents the wavelengths within the spectrum that we can actually see, and we can see it with the human eye. There are other wavelengths we cannot see. And let's go all the way to the bottom and just walk through these, because these are really common like terms that kind of classify a group of wavelengths. So for example, radio waves. You've heard of radio waves, and these go from anywhere down to like 10, there's like hertz up to like kilohertz up to megahertz. And these are radio. And so this is like AM radio, FM radio, but this is also Wi-Fi. Okay, and this is also Bluetooth, and this is also 4G LTE, and this is also 5G. So this is where we do a lot of our communication systems, wireless communication systems, in this wavelength down here. And the wavelengths are pretty big. They range from, this little plot right here shows like how big they are. So it's like a skyscraper is one crest to crest, all the way down to when you get into like megahertz, like your FM radio and your Wi-Fi and stuff like that. You're down to like something that's the size of humans. Like 6 feet, 5 feet. Okay, then you've heard of microwave. Okay, so microwave, turns out, can heat stuff up, primarily water, but it's going to have wavelengths that are kind of in the order of 10 to the negative 2, so like the size of a butterfly. But microwaves, we use those for microwave ovens. I mean, that's the biggest application of it. Infrared. Let's talk about our remote controls here. Infrared is about the size of a needlepoint, and we actually discovered the infrared LED was actually invented before the red LED. So they actually had practical uses for this, doing, short range communication. And I'm not kidding, primarily like remote controls. So your remote control for your TV, whatever you have, remote control, is infrared, okay? And then you get into the visible. And what's neat about this is that depending on the wavelength, it starts with, as it gets shorter and shorter and shorter, you start seeing red. Then it goes to orange, and then yellow, then green, then blue, then violet, and then we go into what we call ultraviolet, which is a wavelength that's actually shorter than what we can see. And ultraviolet is, it's on like getting down to like the molecular band, or the molecular size, so atoms that are joined together. And ultraviolet is used to do a lot of processing of integrated circuits. It's also what makes it through the atmosphere and can burn our skin. But it's also extremely important because it keeps us warm and it gives us some vitamin D. But if you sit out in it too long, you'll burn yourself. Okay, so interesting. All right, then you get into X-ray. X-ray has wavelengths that are like the size of like the atom, so it's really, really small. But they discovered X-rays were really cool because you could shoot it into a human and it would bounce off their bones, and you could see their bones. So obviously X-rays are used for that, but you use X-rays for a lot of other things. You use it for telescopes and scientific measurements and stuff. Then you get to what we know as the highest energy wavelength, which is the gamma ray. And this is down in it's the size of like a proton neutron. It's way, way down there. And I mean, its frequency is 10 to the 20, like so big you even forget the terms for it. So then that's kind of the spectrum. And these like gamma ray, it's not like one frequency. It's a bunch of frequencies. So it's a range of frequencies. So when somebody says the visible range, they're not talking about one wavelength. They're talking about a range of wavelength. When someone says radio waves, it's a range of wavelengths. And then down here, you see this relationship to energy and heat. And so what happens is that as these things have more energy, they basically emit heat. And so the energy of the photon is related to how much heat we can see. Okay, so that is the electromagnetic spectrum. Now the next question is, where do these things come from? Where are these photons coming from? I mean, these are pretty important things. We're using them all over the place. Here's where they come from. Okay, now take a deep breath because this is weird. And it's just counterintuitive the first time you hear it, but here we go. When you have an atom, you have electrons that orbit the nucleus. And Each orbital represents an energy level that that electron has to stay in that orbital. If you impart energy on the atom, the electron will move up into a higher orbital, okay? And that electron is then said to be energized, okay? So if it's cruising around right here and all of a sudden you give it energy and it jumps up to here, it's in another orbital, but it's now energized. It has higher energy when it sits up here. So this is like more energy. Now, over time, what'll happen is that you have vacated the lower orbital. So when this thing basically moves back down, once its energy is like, oh, I don't have enough energy to stay up here anymore, it's going to go, and it'll go back down. And what happens is when it goes down, as soon as it jumps down here, a photon is emitted. Okay? Now, that is pretty dang cool. And it turns out that the wavelength of the photon depends on the material. So depending on whether you're using gallium arsenide or you're using, helium, or you're using like, I don't know, anything, or compounds or molecules, it will give off different photons. Now, the question is, how do you give energy to the electron to excite the electron to move from one orbital to a higher orbital? Well, it turns out you can use voltage. So we love that because we're like, hey, I know that atoms exist in materials. I'm going to put voltage on it and I'm going to get that thing to move up, and then I'll let it not decay, but I'll let it move back down into a lower energy orbital and a photon will be emitted. And so it's like, oh, that's awesome. It's like how an LED works. You can also do it with temperature. And you can also do it with photons. So you can actually shoot a photon in and then it'll give a photon off. So this image right here from Giffer is showing that. So it's like it's energizing the photon or the electron by hitting it with a photon, and then the thing goes back down and it gives off another photon. Now that is like, you can think about that like an LED. So it kind of makes sense, like you build some material, it's a semiconductor material, you put energy across it and a photon's emitted. And the type of material you use will dictate whether it's a red or an infrared LED. Photons also can come from antennas. And so this is where you really think about like, oh, okay, now this is something that's more kind of hands-on. I understand it, because if you take an antenna, which is a conductor, and put it at the end of a circuit, and it has a particular shape and and you drive it with a particular frequency of a source of an AC signal, it has the potential to emit photons. It will actually produce an electromagnetic wave that is then transmitted. The energy is converted from the electrons in the wire, and it'll actually create electromagnetic radiation. Okay, so this is really cool. So this is like how our cell phones receive and send data. This is how radios send and receive data. But it's the same principle. This is a way to like move actual materials and particles back and forth within a material, and that induces electromagnetic radiation in the form of a photon as it goes out. And like I said, depending on the size of the antenna and the source frequency, that dictates how basically what the frequency is of your electromagnetic wave. In general, if you have a bigger electromagnetic wave that you're trying to get, you need a bigger antenna. And the smaller of a wave you want, or let's say higher frequency, shorter wavelength, the smaller your antenna is. Okay, so that's why like old radio towers used to be huge, because they were sending like kilohertz wavelengths, okay, or kilohertz frequency, long wavelengths. Now look at your cell phone. Early cell phones had like antennas on them. They were like 6 inches long that you had to pull up. That's because they were running at a higher frequency so they could use a shorter antenna. Today, your antenna is so small because we're using like gigahertz frequencies for the electromagnetic waves that the antenna for your cell phones are actually inside of your phone. You don't even see them anymore because they're so small. Okay, so that is where the photons come from. Okay, and that is an introduction to electromagnetic waves. So we'll do one more video where we talk about some of the behavior of it, but just in general, that is what they are and how they are used. Okay, we'll see you.